All right, welcome to our next lesson in analyzing two-dimensional collisions. Um, Take a second to review the general outcomes of this topic before we start our example. All right, so here's the problem that we're going to approach. We have two objects, blue and red over here. In the before situation, we have the blue object moving with a velocity of 2 meters per second to the right. It's got its mass, 1 kilogram. We have our red object that's stationary. It's got a mass of 2 kilograms. After the collision over here, we see that the blue object's kind of moving to the right and up, and the red object's kind of moving to the right and down. We're going to use the law of conservation of momentum to analyze and try and solve for the quantity, what is the velocity of the red object after the collision. As before, we're going to use a vector diagram to show the conservation of momentum. In this case, we have, I'll just sketch it up quickly, we have the momentum of the blue object before the collision, which is really the total momentum before the collision. Then we have the after situation in which the blue object's moving this way with some momentum, blue object's momentum after the collision. And that's going to be added tip to tail to the red object's momentum after the collision. Draw it like that. And if I've drawn this somewhat closely, we'll see that the momentum before and after, if I slide these things together, these momentums after the collision should be pretty close to the momentum before the collision. If they aren't on my diagram, I can alter them a little bit to show that that's indeed what should happen. That is the law of conservation of momentum, that the two vectors drawn after the collision should add up to the momentum before the collision. Now, probably the most important thing to do when you start one of these problems is really draw a good vector diagram. It's probably as important as, I talk about drawing a sketch of the situation, make sure we understand it. To really apply and use the law of conservation of momentum, and to not make mistakes when you're doing a bunch of calculations somewhere along the road. Drawing a good vector diagram is really critical. So I'm just going to draw this really a little more carefully, a little larger, so I can do some calculations right on it. There's my momentum after the collision of my blue object. Here is the momentum after the collision of the red object. And prior to the collision, here's my blue object's momentum. Momentum of the blue object, oops, before the collision, no symbol there. Now I'm going to label as many parts of this as I can right off the bat. I have an angle right here from the description of the collision of 30 degrees. I'm not going to assume anything about the angle of the red object. I think that would be a mistake. We can't assume that it makes it a right angle triangle as we've seen in the past. Sometimes it does, but let's not assume that it's going to do that. Now we need to label some numbers on here in terms of the momentums before and after the collision. So let's go back and take a look at what the momentums were. You can see from the before situation that the momentum of the blue object, its mass times velocity, is going to be 1 kilogram times 2 meters per second, or 2.0 kilograms times meters per second. Let's put that on our diagram as our before momentum, 2.0 kilograms times meters per second. Let's take a look at what we know after the collision. After the collision, the blue object here has a momentum equal to its mass times velocity. Nothing in the question suggests it lost any mass, so it's 1.0 kilograms times 1.5 meters per second. So it's 1.5 kilograms times meters per second worth of momentum at an angle of 30 degrees from the right. Let's write that down here. This side of our triangle is 1.5 kilograms times meters per second. So as you can see, by going back, labeling this diagram the best I can, drawing it to scale, or not to scale, but drawing it in such a way that I can now see that this really becomes a math trigonometry problem. I have two sides of a triangle, and I'm missing the third. Now you have two approaches to this question. One is for those people who like it, and it's on your data sheet. You can use the law of sines and cosines to solve for the two. Remember, there's two things we're looking for: the magnitude and the direction of our vector. So we can use the law of sines or cosines, and that's fine. The way I'm going to go ahead and solve this is I'm just going to do an analysis of the vectors and make sure that when they come together, all the momentum in the x-coordinate and all the momentum in the y-coordinates, those things add up. To do this, as carefully as I can, I'm going to actually draw each of my vectors a little separately. So here's my blue vector after the collision. Notice that the blue vector after the collision has two components. If this is 30 degrees and this is 1.5 kilograms times meters per second, I'm going to do this quickly, but you can check my math. But if you use trigonometry, you will find that it has the following value. The x-coordinate is 1.3 kilograms times meters per second. That's to the right. And then the y component is 0.75. So looking back at my diagram, I hope it's obvious that if the blue vector has a momentum after the collision up at 0.75, then the red vector, which I can draw separately over here, the red vector should also have a momentum down at 0.75, because before the collision occurred, we had no momentum in the north-south or in the y component. It was all to the right. So our positive 0.75 here combined with our negative 0.75 here means that momentum in the y-coordinate is conserved, and it's 0. Likewise, on our diagram, if the blue momentum is 1.3 in the x, that means that this part right here is 1.3 kilograms times meters per second. Notice that on our diagram, the total momentum from here all the way to here is 2.0. That means that the red vector, the red object, must have some momentum to the right equal to the difference between what we started with, 2 kilograms times meters per second, and what we ended at for the blue object, 1.3. So the missing amount right in here is going to be 0.70 kilograms times meters per second. So on my red diagram down here, I'm going to draw 0.70 units of momentum there. So our goal was to find the total momentum, magnitude, and direction of the red vector. I've done that essentially here. All I need to do now is apply Pythagorean theorem, a squared plus b squared is equal to c squared, and use trigonometry to find an angle. Ideally, I guess I would find this angle here because it's relative to the original direction, which was to the right, but I could certainly find this angle as well. I'm going to skip to the answer right now, and you can check my math and do it for yourself. But I think that the answer is this. In terms of magnitude, 1.1 kilograms times meters per second. In terms of direction, I find this angle to be 43 degrees, which would mean this angle is about 47 degrees. So my final answer for the momentum of the red object after the collision, 1.1 kilograms times meters per second, 47 degrees down from the original position. So I could say maybe down from right. And that would probably be an accurate description. If we had north, south, east, west, we would use that. So in summary, we're looking at using the law of conservation of momentum to solve for a two-dimensional equation in which we don't necessarily have a right angle triangle. The way around that is to draw a vector diagram so that we end up with a triangle that we can either use the law of cosines or sines, or resolving the vectors into the x and y in order to ensure that momentum is conserved in the x and that momentum is conserved in the y. And by doing that, we can find the final momentum, in this case of the red object. And if we want to, we can convert that to a velocity.